Okay. So we begin with the stoichiometry of chemical equations, and the central question is, what can be calculated from a chemical equation? Now, as shown in the handout, we're using the equation for synthesis of ammonia, 3H2 as a gas, plus N2 as a gas goes to 2NH3 as a gas. And so we want to again ask ourselves, well, what can I numerically obtain from a chemical equation? And the list is very straightforward in terms of what you can calculate: moles and mass. In general, that's equation mass. Right there. Particle numbers. Just a little bit here. Particle numbers, gas volumes, and energy values. So when we look at the equation given, the coefficients of the balanced equation are essentially moles, and you can just simply write 3 moles of hydrogen, molecular hydrogen, 1 mole of nitrogen, and 2 moles of ammonia are produced out of the reaction. Well, that's pretty straightforward. Well, this is what we call the standard equation. The standard equation is an equation whose coefficients have been reduced to the smallest whole number ratio. Now, we can multiply through by 2, divide by 2, or divide by a number, or multiply by a number, and the equation's still valid. But in the basic sense of the equation and definition, it is referred to as a standard equation when the coefficients are reduced to the smallest whole number ratio, as shown in this example. Now, when we talk about moles, we also talk about molar mass, and when we talk about mass as it applies to equation, this is what we call equation mass. The mole weight of hydrogen, for example, as many of you already know, is 2 grams per mole, but indicating 3 moles by the coefficient, that is 6 grams of hydrogen. And nitrogen, coefficient is understood to be 1 there, so that is 1 mole of molecular nitrogen. Nitrogen's 14 on the periodic table, atomic mass units, and twice that's 28. So we have 28 grams of the nitrogen from the equation. And ammonia the same way, 2 mole weights refers to 14, 15, 17, and so that's 34 grams. So 3 moles plus 1 mole always produces 2 moles. Our 6 grams, which is 3 moles of hydrogen, 28 grams of nitrogen molecular, produces 34 grams of ammonia. Now, particle numbers has 2 definitions here. And one is just, we're talking about 3 molecules of molecular hydrogen, or 1 molecule of molecular nitrogen, or 2 molecules of ammonia. Now, that's one way to look at it. Now, it also relates to the Avogadro's number. And you recall Avogadro's number is 6.02 times 10 to the 23rd. So there's 6.02 times 10 to the 23rd particles in a mole of each one of the substances in the reaction. So that's the second way to look at the particle numbers. And we look at this as 3 Avogadro's numbers of molecular hydrogen, or we look at 1 Avogadro's number of molecular nitrogen and 2 Avogadro's number of ammonia molecules, as shown here. So if for whatever need you might have, you need the absolute numbers of particles from the reactant or something. Moles times Avogadro's numbers gives you that value. Now, gas volumes in here depend on specific temperature pressure specifications given in the standard equation. And there are 2 standards that you'll run into in this. One is what we call the gas law standards, and then another one is the thermodynamic standards, and they only differ by temperature. The gas law is 0 degrees Celsius and 1 atmosphere, but thermodynamic standards is 25 degrees Celsius and 1 atmosphere. Now the thing about taking this into consideration, gases expand when you heat them or compress when you cool them. So that if you're talking about the standard gas law conditions, you can specify a specific volume of, say, a hydrogen or nitrogen or ammonium based upon that temperature pressure condition. Now, if you're talking about standards in thermodynamic terms, you would have to use larger volume values because you're at higher temperatures. So that's an important consideration when dealing with calculations. I'm going to move this up and say some more in here. Now, in terms of the coefficients in relationship to moles, a mole of gas is called a molar volume. And we typically note that as a capital V subscript M. And by definition, this is the volume occupied by 1 mole of any gas. It doesn't matter what the chemical composition of the gas is. 1 mole, regardless of the gas, always occupies this same value. Now, to specify a value, a numerical quantity, such as liters or milliliters or so forth, gallons or whatever, you have to specify the temperature. At standard conditions called STP conditions, that's your gas law standards, I'll put it again, 0 degrees Celsius, 1 atmosphere. 1 molar volume is equal to 22.4 liters. Now at thermo 25 degrees and 1 atmosphere, 1 molar volume is about 24.5 liters. See how it expands because we're working at a higher volume. Higher temperature, sorry. At a higher temperature. So you have to take that in consideration. Now, having said that, the issue that you are going to face in working with stoichiometry is as the equation is written. Now, when I say that phrase, as the equation is written, so it's not going to have a little subscript over here that says this is thermo or this is STP. Now, sometimes they will. But if it doesn't say anything about thermodynamic standard or STP, you assume the standard STP conditions for the standard equation. So having that in your mind, you can say this is 3 molar volumes times 22.4, or 1 molar volume times 22.4, or 2 times 22.4. Now that is a given relative to the temperature pressure specified in the standard equation. I'll put that standard equation is how that is written. So as we move through this, this is 3 molar volumes, if you can I'm losing my equation up here. I don't want to. You can see that down here. It says 3 molar volumes, 1 molar volume, and 2 molar volumes for the ammonia. And remember, and I emphasize this again, you can only put a number for the VM if you specify the conditions, the standard conditions. Okay, any questions about that? So it's just a relative relationship, but it is very important that you consider that when making various calculations, and we'll run through one here in a few minutes. Oops, I'll try that again. When you take into account energy factors, there are 2 types, and we'll see this over and over, of equations that relate to energy, and that's endothermic, exothermic. Well, actually, there are 3, isothermic. But the 2 that are most dominant are endothermic and exothermic. Well, thermochemical equations as they are called, can be written with energy numbers attached to them or associated with them. And there are 2 forms that you will see as we go through the course. Let's start with exothermic first, because that's what the example equation is. So we've given an equation, 3H2 as a gas plus N2 as a gas going to 2NH3 as a gas. Now there are 2 ways to write energy numbers into the equation. One is detached and one is included. Detached, you'll make a semicolon and a delta H, which means the enthalpy, heat of reaction, standard heat of reaction. And is referred to as enthalpy. And that is equal to, in this case, 91.8 kilojoules. Okay. So we have separated the energy number from the equation. Now, a second way to write this is incorporating the number into the equation. If it is exothermic, you incorporate that number on the product side, and showing here. Now, while this is exothermic, it's indicated by having a negative sign in front of the numerical value right there. That says exothermic. But what says exothermic in this second example here is that the number is posted on the product side. It means it's liberating energy from that system. So these 2 are mean the same thing energy-wise. Both are exothermic. Both have energy numbers that are identical, of course, but one is incorporated into the equation on the product side and indicates exothermic. And what it means that if you react 3 moles of hydrogen, 1 mole of nitrogen, 2 moles to produce 2 moles of ammonia, you will obtain 91.8 kilojoules, essentially, from the standard equation is written like that. So that's a short notation on how to write and illustrate exothermic. Now, endothermic reactions. So now, an endothermic reaction is a reaction that's absorbing energy, and one example is evaporation. If we take water in the liquid form going to water in the gas form, water vapor, then you can write delta H is equal of reaction is equal to 44 kilojoules. Now, notice it is endothermic because it is plus. Now, you do not have to write the plus symbol into the notation here in the symbology, The fact that there's nothing there indicates it's positive. If it's the other case, of course, it'll be a little minus sign there. Now, when we incorporate the energy number into the equation as an endothermic, we must put that on the reactant side. So the equation that incorporates it incorporates the energy number, would put it on the reactant side like this, and show the production of the 1 mole of water vapor. So in its interpretation, it says 1 mole of water, liquid water, requires 44 kilojoules to absorbs 44 kilojoules and converts the 1 mole of water into vapor phase. So what I've tried to do is give you a cross-section of what can be calculated from chemical equations. And so the essence of this is to orient you with how to start chemical reaction problems. And so right now we want to get into working some problems that relate to the stoichiometry of these equations. So let's start with stoichiometry of chemical reactions. Let's start with a simple reaction, a combustion reaction. Methane gas reacts with 2 moles of O2 gas to produce 1 mole of CO2 gas and 2 moles of either water vapor or liquid. You can list it either way. Sometimes it comes in as a gas and sometimes it comes in as a liquid, but they're still the same essential equations. So let's say you're given 60 grams of CH4. How many grams of water will be produced? This statement is very important that you understand. When working chemistry problems, there are several ways to approach these. Dimensional analysis is one, inspections another, and so forth. What I tell people, and I find that ratio and proportions and inspection relationships can be best served by converting all given data to moles and then applying it to the equation and equation ratios. What I mean by that is this: convert data to moles, solve the problem, and at the end convert to needed dimensions, whether it be gas volumes or whether it be mass quantities or energy numbers or whatever. Start out with the moles of the substance and then solve the problem in terms of moles. So what I'm saying is, what we want to do is take 60 grams, convert it to moles, and see how the relationship is between moles of methane and the production of moles of water. So 60 grams of methane is 60 grams divided by 16 grams per mole. That's 1 mole weight. So in our calculator, we see 3.75 moles of the methane gas. Well, when we compare the moles in the standard equation to the moles yield of water, we find it's a 1-to-2 ratio. For every 1 mole of methane, we get 2 moles of water. So that means 3.75 moles of methane will give 2 times 3.75 moles of the H2O water vapor or liquid water, or however you want to count it. So that works out to 7.5 moles of water vapor. So convert to moles, solve by ratio, and then convert to something that it might want. Now it asks for how many grams of water. So grams of water now, to convert back from moles, you multiply times formula weight. So water has an 16 plus 2 is 18 grams per mole. So 7.50 gram yield times 18 grams per mole. Moles cancel. That should be 7.5 moles, not grams. Moles gives us, okay, so that's 135 grams of water vapor generated. So that shows you how we start these. Convert to moles, solve by ratio, and then convert back to whatever dimension you need. Now, let's say the same problem, given 60 grams of methane, what volume of water vapor gas is generated in this problem? So that's the second problem in this. Okay, so I can add to the problem something of this nature. It says calculate the volume of H2O gas produced at, and I have to specify a temperature pressure, which is in this case 0 degrees and 1 atmosphere, which is standard conditions. Well, at STP conditions, 1 molar volume is always 22.4 liters at STP conditions. So if we scale it up to 3.75 moles, then 3.75 moles of water vapor is equal to 3.75 molar volumes at STP. That will certainly be 3.75 times 22.4 liters per mole, and of course that is 84 liters at STP. Yeah, I picked the wrong number up here. I should have picked the 7.5 moles of water. Now, what do you do if you're not at standard conditions? Now, this kind of reaches over into the gas laws, the Boyle's law and Charles' law kind of thing. So let's work this problem out in terms of non-standard conditions. So I'm going to add another one. So let's calculate volume of H2O gas at 25 degrees Celsius and 740 millimeters of pressure. Okay. The way I tell people to do this is adjust it by what we call a standard ratio. How does the gas behave? How does the gas behave if you raise the temperature or lower the temperature? Or how does the gas behave if you increase or decrease pressure? Well, increasing temperature increases volume, whereas increasing pressure decreases volume. So that's a Boyle's law. That's an inverse relationship. So what I tell people to do in cases like this, well, all gas laws need to be converted to Kelvin, worked in Kelvin. This is 298 Kelvin, 273 plus whatever Celsius value you have. So the volume at 25 degrees C and 740 millimeters is an adjustment. Now listen to what I'm saying. Adjustment of the standard volume that you have by the changes that are specified. An adjustment of given standard is we're going to adjust 168 liters due to temperature change and due to pressure change based on going from standard to a new condition. So we really have two ratios, standard to new conditions, standard to new conditions. So that ratio, say the temperature factor, okay, what have we done here between 0 degrees and going to 25? Well, that's obviously an increase in temperature. Well, what's the gas going to do volume-wise? It's going to increase. So what that says is, let's use a ratio of the conditions to the standard that'll give me a bigger number here. I need to increase this number. And so that looks like this, 298 Kelvin over 273 Kelvin, because that's the Kelvin value for standard. Now, if I use 273 over 298, that's going to give me a smaller number. Well, that's not what's happening. What's happening is you're increasing volume in this case. Now, in the pressure effect, 740 is below the standard. So you're decreasing the pressure. Well, Boyle's law said if you decrease pressure, volume has to increase. So the standard number here, this 168, has got to increase by a ratio of standard to new conditions. To increase, I have to have 760, which is the 1 atmosphere, over 740 millimeters. And of course, those will inherently drop out. And that will be an adjustment. That's the shortest way to the new volume. I get 188. Don't back me up on this, somebody. So if I make a mistake, I want to fix it. Without going through all the gas laws, that's the simplest way to deal with it. Okay. Let's say you're given the 3H2 gas plus N2 gas going to 2NH3 gas, and you have 91.8 kilojoules as the given equation with its energy number. Calculate change in actually delta H of the reaction for, I don't know, 20 grams of H2 mixed with 20 grams of N2 gas. Now, the procedure that I emphasize is convert to moles and then solve the problem in terms of moles and then convert to whatever you need in that case. But in the process of solving the problem, we first have to see what a limiting reagent is. And you'll hear me use limiting reactant, and it's the same thing as limiting reagent, but it is always on the reactant side, so people use limiting reactant. It is the compound in the reaction that when consumed, reaction stops. It's very easy to determine the limiting reagent or reactant in any of the problems simply by convert to moles, divide by the respective coefficient. The smaller number is always a limiting reagent. Okay, what did I say? Okay, first convert to moles. Okay, so if we have 20 grams of molecular hydrogen, then I need to divide by 2, and that gives me 2 grams per mole need to be complete, 10 moles. And if I divide by the respective coefficient, that's 10 over 3, I get 3.333, like that. So in the same context, nitrogen, if we have 20 grams of N2 gas, then I'll divide by 14, and so 20 over 14 is 1.43 moles. And then I divide by respective coefficients, so 1.43 over 1, see, is equal to 1.43. So the smaller of those two numbers is the limiting reagent. And everything depends on production around that, because what it says is you'll have hydrogen left over. You've got more hydrogen you need in the reaction. You'll only use, actually 3 times this 1.43. So if you have 10 moles, you're going to use 30 moles in this entire reaction. But it's a very simple way to determine the limiting reagent in here. So by the context of the problem, we have 1.43 moles of nitrogen consumed. We're using that. We don't care what the hydrogen's doing, because it's the relationship between moles of nitrogen and this energy number that governs the problem. So 1 mole of nitrogen produces 91.8 kilojoules. What will 1.43 produce? Well, obviously, it's 1.43 times 91.8. Now, that's obviously kind of sarcastic, but 91.8 kilojoules. So you can hopefully see 91.8, and so that's 131 kilojoules. 131 kilojoules is the yield of that reaction. So convert to moles, identify the limiting reagent, and work the ratio around the limiting reagent. I'll say it again. Convert to moles, identify the limiting reagent, divide by respective coefficient, smaller number is your limiting reagent. Work your ratio by the limiting reagent, and you'll convert to moles. Now, if they want something else, and it's not really a lot of something else in the energy numbers. They might want it in joules or something, times 1,000. But the essence of it is comparing moles of reactant to product, or moles to energy numbers, is probably the most direct way I can teach in this. Now, of course, there is dimensional analysis, and some people are hung up on it, but if you can master this, you can master a lot of the problems in chemistry very quickly. Solutions, by definition, is a homogeneous mixture. 3 stripes is by definition. They're physically prepared and they're physically separated. That means using physical properties. You mechanically mix something together to make a solution. And solutions result from blends of states of matter, solids and liquids and so forth like that. But when we talk about making solutions, we're talking about a combination of something you're dissolving into something that is acting to dissolve whatever you're dissolving. And those are identified as a solute and solvent. So the composition of a solution is a solute plus a solvent. And of course, as you probably already know, the solute is the component in the smaller amount, and the solvent is the component in the larger amount. combined that makes up the solution overall. Solutions are typically expressed in concentration terms. Of solute in solution. Now, please note what I didn't say. I said concentration of solute in solution, not solvent. So this is, you're having an amount of solute in an amount of solution, which is a combination in here. Now, there is a case in which you will use solute in an amount of solvent, because there's a thermal history that the system goes through, and that's not here. Everything we're going to be doing right now is assumed to be at one temperature, so it's solute in solution, the combined amount. So when we define concentration, by definition, it's an amount of solute in an volume, in this case, volume of solution. Actually, it's an amount of solution, but we're expressing everything in volume terms. Okay, so this should be pretty obvious to you in terms of this definition. Now, there are many solution concentration terms. We're not going to mess with all of them. What we need is molarity. So expressing solutions in terms of solution concentrations in terms of molarity is our focal. So molarity is given by capital M symbology, and by definition is moles of solute in volume of solution expressed in liters. Moles per liter is what most people say. Keep it simple. Now, why is this an important issue? Because it is the mechanism, it's a definition. From this definition, you convert what we call solution data into moles and apply to the chemical equation. So from this equation, moles over volume of solution, solve this little three-part equation for moles. So this gives us moles of solute, which is important in solving the equation. Well, the solute is molarity times volume expressed in liters. Molarity times volume is moles. Molarity times volume is moles. Please memorize that with all due diligence. Because why? You're going to be given problems that relate to equation solutions that you need to convert to moles and solve the problem, and then convert back to whatever you need. And you'll see how this works out as we get deeper into this. Okay, let's say you're given the following equation. HCl aqueous, that means it's in aqueous solution, plus sodium hydroxide aqueous goes to sodium chloride aqueous, plus the driving force H2O as a liquid. Now, let's say you were mixing 25 milliliters of 0.12 molar HCl with 28 milliliters of 0.09 molar sodium hydroxide. That's your mix. So you got two beakers with these quantities, and you pour them together. Now the question is, what is the limiting reactant That's 1. And how much excess reactant remains. So you need to read through and, analyze problems like this. This is what you're going to be doing in lab work. And I'll get to that in a couple of minutes. Now, the focal point of this is on the reactant side. So this is a method of calculation that I try to emphasize to students to simplify and try to keep things organized, more or less keeping your bookkeeping straight. So what I'm going to do here is I'm just simply going to take and write down the given 25 milliliters of 0.12 molar HCl plus the 28 milliliters of 0.09 molar sodium hydroxide, like that. And I didn't write the product side in there, if you notice. So what does this mean in terms of a calculation? Well, convert to moles. Well, how do you convert this to moles? When you see numbers like this in data that's given, you're talking about these two being together. That's called solution data. Right there. Here's a set of problems out of Ebbing that deals with volumetric analysis, as they call it, and contains data that will deliver to you in the form of what we call solution data. And here's one that's emphasized. What volume of a 0.250 molar nitric acid solution reacts with? See how this data comes in as a volume and a concentration term right there? And that's called, when you see them together like that, is solution data. And it should strike you as the device through which you will convert to moles. Molarity times volume in liters equals the moles of the reagent you're working with. Molarity times volume is moles. So that's why I'm showing you this. So the thing I want to do is convert this to moles. Well, what does that mean? Molarity times volume. So that's a 0.025 liters liters times 0.12 molar. That's moles per liter. So liters will cancel out and you're left with moles of HCl plus 0.028 molar, let me do the liters, 0.28 liters times 0.09 molar of sodium hydroxide, right there. So when I multiply those together, I will have the data given in moles, and then I can relate it to the equation here. See, this is your HCl and this is your NaOH. So we have 0.003 mole of HCl plus 0.0025 mole of the sodium hydroxide. Now, as you look at this, now this is now, this data now is in terms of moles, so we have 0.003 mole, and this one also has been in moles, so that's 0.0025 mole of the sodium hydroxide. Now, if you compare moles to moles and look at the reaction ratio, it's a 1-to-1 reaction ratio. Well, you divide by the respective coefficients, then the sodium hydroxide is your limiting reagent here. As you look at this, then how much of the HCl will react? Well, you'll only, since it's a 1-to-1, if you use 0.0025 mole of sodium hydroxide, you're only going to use 0.0025 mole of the HCl. That's it. Everything else is the excess. How much excess will be left over? And you can figure that in terms of moles. Okay, so let me move this up a little bit here. So, limiting reagent is the sodium hydroxide, and the excess HCl will be 0.0030 minus what is used, which is the same as how much sodium hydroxide is used, because it's a 1-to-1. Everybody okay on that? Some people miss that, and it causes problems later on. So I want to simply subtract 0.0025, and that leaves me with the moles of HCl in excess. That up, we won't need that anymore. That gives me 0.0005 mole HCl excess. What is the concentration now of the HCl? It ain't just moles. Moles and molarity are not the same thing. Moles is a mass number. It is the mass containing one Avogadro's number of particles. Molarity is a concentration term. It is a moles per liter issue. So if I have 0.0005 mole HCl, how do I convert that to a concentration term? Well, first of all, you have to look at applying this to the definition of molarity. And keep in mind that we mixed 25 and 28. So you have now a solution 53 milliliters. So you've mixed that. So milliliters is your volume number, and your moles is your mass number. So molarity is moles over liters, moles over liters. And so the concentration, and you'll see this also, these brackets like that, that means moles per liter, and it's used extensively as you go forward in this. So that means molar solution. So you want to get comfortable with that very quickly. So the concentration of HCl is moles of HCl remaining, that's the excess, divided by the volume of solution expressed in liters. And so you mix 25 and 28, which gives you 53, and that's a 0.058, excuse me, let's see. 53, yeah, 3 liters, and the moles is 0.0005 mole per liter. And so your concentration remaining of excess HCl is roughly a 0.01 molar in HCl aqueous solution. That's your concentration as you apply. And you will run into this many times as we go through. So what did I do? Okay. I converted the moles by molarity times volume, applied it to the equation and determined who's excess, and then converted that excess into molarity. The question is, what volume of Nitric acid will react with 44 milliliters of 0.15 molar sodium carbonate. Here's your equation. Is 2HNO3 aqueous. I'm going to leave the aqueous off. It's all in water. Sodium carbonate. And that goes to sodium nitrate plus water and CO2. Like this. Okay? Now, it's given, the question is, what volume of 0.25 molar will react with 44.8 milliliters of a 0.15 molar solution of the sodium carbonate, like that. When you look at this is a 2-to-1 ratio. Now, here's some stoichiometry you need to be aware of also. In just looking at the standard equation, what's the reaction ratio here? 2 parts acid to 1 part sodium carbonate. 2-to-1. So what can we say about the moles of nitric acid? So moles of HNO3 used is greater than the moles of Na2CO3. You agree with that? Everybody, look at this statement, please. From the equation, the moles of nitric acid is greater than the moles of sodium carbonate in the equation. Yes? That's pretty easy to see. Now, what if I want to make those equal? What would I do? I would take the moles of HNO3 and 2 times the moles of sodium carbonate. That, now they're equal. Because I double whatever this is, it's going to be whatever you used over here. Because it's a 2-to-1. And that's tricky. So look at what I did. Yeah? I can make these equal. Well, what is moles anyway? How do I get moles out of solution data? Well, molarity times volume expressed in liters of the HNO3 has got to now be equal to 2 times molarity times volume in liters of the sodium carbonate. See what I did? Now look at your data that's given. Put it into that formula and solve for what they're asking for now. Look at the data. So I gave you a 0.25 molar, so that's 0.25 molar, and we're looking for volume in liters, and you can convert to milliliters, you know, after the fact. And then you have 2 times the molarity, which is 0.15 molar, times volume in liters, if you want to keep it that way, 0.0448 liters. Now solve that for the unknown. And all you're doing is really applying the concept of convert to moles and apply it to the equation. See what I did? You follow me? So, volume in liters used is 2 times 0.1, sloppy, 15 times 0.0448 divided by 0.25, and everything's going to come out in liters in this case. 0.54 liters or 54 milliliters, multiplied by 1,000. So this is just an example, but the issue is recognizing how to take solution data, which is the focal point of many problems we're about to get into, and convert it to moles so you can apply it to equation ratios. That's the focal point. And that handout I've given you's got several problems in there that you try to get to.